This is our last chapter for the semester, chapter 9, and we'll be looking at nuclear chemistry, a very important topic in chemistry and in everyday life. So let us start our discussion, and what we'll be looking at in this chapter is some of the properties of the nucleus. Remember, we studied the nucleus earlier in the semester. Then next we'll look at nuclear radiation. So that's going to be something new for us. We'll define nuclear radiation and we will apply that. And then we'll look at the particles of the nucleus. We've already covered some of that earlier in the course. And next we'll look at the energy of the electromagnetic spectrum, or the relationship between the energy and the nucleus. And lastly, we'll look at reactions involving particles of the nucleus. Okay, so a bit of history, just to show you the development of science to the stage where we are today. Way back in the 1800s, as you read your chapter, you will quickly observe that. Way back in the 1800s, what was observed that there are some elements that behaved a little differently from others. And Berkeley took uranium salt and he put it in a box, a lead box, and put a little hole, a little slit in that box, and he also put two electrodes, a positive and a negative. And what he observed is that if he had a photographic plate back here, something that could detect light and radiation, what he observed that if this was all enclosed in a dark box where there's no light, so he would not expect any development on the photographic film. But what he observed was that there were some images on the photographic film. He also observed that there were some on this side which he concluded were attracted because of the positive nature of the electrode here. So he concluded those were negatives because, of course, as you know, negatives attract to positive. He also observed way over here that it was bent, and there were some particles that were bent towards the negative electrode. So he concluded those have to be positive because at that time they knew that opposites attract. And then he observed that there were some particles that went right through. It did not attract to any of the electrodes, just passed right through. So he assumed that was neutral or did not have an effect from the electrodes. So he concluded that they were particles because they were developed on his photographic film. So let us define what these particles are and see their reactions. So the particles that he observed and later defined were, one was the alpha particle. Before we do that, however, let us define nuclear radiation. So nuclear radiation is emitted from the nucleus during a reaction. We'll call that reaction a nuclear decay. So he observed that this was not really light being projected on the photographic film because it was in a black box. There was no light. So there had to be something different from light. One particle was the alpha particle, and this is defined as the helium nucleus, which contains here 2 protons and 2 neutrons. Again, the protons here are different from the protons of your acid-base reaction. These are the protons or the particles in a nucleus. Another particle that he defined was the beta particle. Notice the Greek letter, beta. And notice a negative here. So this beta particle has a negative charge. As you saw from the previous experiment, it was attracted towards the positive electrode. Another particle he observed was the positron. Notice again, it's positive. It has a positive charge. And another particle, another aspect that he observed was the gamma ray. This was the one that went right through and was not attracted or by the electrodes. Went right through the center. There was no deflection. So these are the four particles that we will examine for the next for the next few slides. The alpha particle, the beta particle, the positron, and the gamma ray. Before we do that, however, let us look at energy. So energy can be described as waves. Can be described in terms of waves. And as you know from your physics class, you have a wave here, so we have a wavelength. So the wavelength is from one crest to the other. And we can have a short wavelength here, or we can have a longer wavelength here. What you will observe is that the shorter the wavelength, the more energy is involved. The frequency is another term that's used to describe these energies, and the frequency is the number of crests that passes in a given time, typically per second. So if you were standing right here and you started your stopwatch, the number of crests that passes in any given time would be the frequency of that wavelength. So we have two ways of defining the energy that's transmitted through waves. First, the wavelength and or the frequency. Okay, let us see the relevance here. So if there are very short wavelengths in this region here, these are the gamma rays and the X-rays. Notice very short, 10 to the negative 10 meters. It's a very short distance. And of course, as you know, these X-rays are high energy, and we try to minimize our exposure to X-ray because of the high energy that's involved. As the wavelength gets longer, however, here's a visible light. Of course, we know visible light is not dangerous to us. UV is, because it has a shorter wavelength, but visible light and going in this region here, it's not, because we have a longer wavelength. The energy of these longer wavelengths are not as high as those in the shorter wavelength region of the electromagnetic spectrum. So this is called the electromagnetic spectrum, which gives you the relationship of the wavelength to the energy. Okay, let's do a quick review here. So most elements that you find on the periodic table that of course exist on Earth are a mixture of isotopes. And you may recall from way back in chapter 2 or 3, isotopes are atoms with the same number of protons but different neutrons. So if you have carbon element, you can have carbon 12, which has 6 protons and 6 neutrons. There's also possible to have carbon 13. That's an isotope of carbon. 6 protons, notice same 6 protons but more neutrons. You can also have carbon 14, which has again same 6 protons and of course 6 electrons, and now we have 8 neutrons. So these are called isotopes. Isotopes are elements that you find on the periodic table that have the same number of protons but different number of neutrons. Continuing with our review, the mass number is the number of protons and neutrons. So of course, as you know, as chemists, we tend to communicate using different terminologies. One terminology here is the mass number of carbon and also the atomic number of an atom. The atomic number is the number of protons. The mass number is the number of protons and neutrons. So the way that's expressed in chemistry is the C here is the symbol for the element. The number that's as a subscript is the atomic number, or the number of protons, and the number that's a superscript would be the number of protons and neutrons. So by subtracting these two numbers, you can get the number of neutrons. So don't forget this notation that's used in chemistry to reflect here the isotopes. Okay, let's try to get back to the relevance here. So there are about 300 naturally occurring isotopes. Okay, so not all of the elements on the periodic table have isotopes. There are about 300 occurring naturally isotopes. And we describe those as radioactive because they give off radioactivity. They give off radioactivity. Just to give you some examples here is carbon 6 and 12 as one isotope. Here's oxygen 618 and some others here. In this case, these are described as pretty stable isotopes. They do not give off radiation. Others, however, the heavier ones, they tend to be radioactive. One that's pretty heavy but also stable is lead. So now you can see why in that early experiment they used a lead box, because it's pretty stable compared to the other elements that have a higher atomic mass. So the elements with larger atomic mass, they tend to be radioactive. Okay, let us look at some of the reactions now. So this time we look at the emission. Remember here, emission means given off. So the emission of the beta particles. So we know what the beta particle is because we know it's a negative, the charged particle. The way it is written though, it's like this. E for electron and -1 and 0. So that's the symbol that's used for the beta particle or the electron. So here, let's look at a reaction. So here we have phosphorus. Isotope of phosphorus, where there are 15 for the atomic number and 32 for the mass number. That's one isotope of phosphorus. If this isotope here emits this electron or beta particle, what is left after that emission? The key here is that the atomic number, this number here, must equal on the reactant side to what's on the product side. So here we have 15 on the reactant side, and we have a -1 that we know is emitted from the beta particle, -1. So a -1 and 16 is equal to 15. So we know that after the emission of the electron, this element here, the atomic number is 16. Let's look at the mass number. So it's 32 here. It emits electron, but this is 0. So this number here and this number here will be the same. You look at your periodic table and you determine what atom has 16 electrons. And when you do that, you'll discover it is sulfur. So phosphorus, this isotope of phosphorus, 1532, it's radioactive and it emits a beta particle, written like this, and after the emission of the beta particle, it forms this isotope of sulfur. Okay, so let us look at another application here. Carbon-14, an isotope of carbon. So that's carbon 6 and 14. Remember, we had three isotopes of carbon, 612, 613, and 614. As you will see later on, 614 is used for carbon dating. But the question now is, if we have this isotope of carbon, it emits a beta particle, and here's the beta particle, so it's a beta emitter, What is this that's left after it has emitted the electron? Again, as we said, here is 6, so these numbers here, whatever number you put here, minus 1 must add up to 6. So right away you can imagine that has to be 7. So plus 7 and minus 1 is 6. This is 14. This is 0. So whatever number goes here will be 14. Let us see what the answer is. So here it is. So carbon 6 and a minus 1 for the electron. So what's left behind is 7. 14 for the mass number. And since this is 0, this is 14. But since we know that the number of electrons determine the element, you look at the periodic table and you'll see that 7 for the atomic number corresponds to nitrogen. So over time, this isotope of carbon, carbon 612, is converted to nitrogen 714 isotope and emits here an electron. Let us look at another reaction, an alpha emitter. So first of all, we'll have to define what is an alpha. The alpha particle is this, a helium nucleus. So it's helium 2, 4. So if we have uranium, of course, as you have seen on the news and know, that uranium is a radioactive material. And this isotope of uranium is a very reactive isotope. So uranium 92 238. Notice it's pretty heavy. So if uranium is radioactive and it emits this, the question is, can you determine what is left after that radiation? So again, we have 92 for the atomic number, and it emits a particle that has 2 for the atomic number. So 90 and 2 is 92. So this has to be 90. 238, it emits helium, and here is a 4. So as you can imagine, 238, if you had 234 and 4, this adds up to, these two numbers here add up to 238. So this is the element that's formed, uranium, after uranium has emitted an alpha particle through radiation. Here's another example. So we have PO, and here's the isotope. It emits an alpha particle. It also emits gamma radiation. Notice there are no numbers here. So therefore, there we cannot subtract anything because these are zeros. So what can you determine? So can you determine what this is if you were given that as an unknown? So we have here 84 and 2. So this has to be 82 because 82 plus 2 equals 84. For the mass number, we have 210, and it emits 4, helium which has 4. So 4 and 206 is 210, so this is the unknown here. Let's see if we can apply this question a little differently here. So what is the atomic number? So now you have to remember what's the different definition of atomic number of the element produced when an element with an atomic number Z emits an alpha particle. So here's the alpha particle, 2 and 4. So by emitting an alpha particle, this number here corresponds to the atomic number. This number here corresponds to the mass number. But here we're asking for the atomic number. So you can see that 2, more than likely, it would be -2 since it is emitting. It emits that or gives off. So let's see what's the answer. As you can imagine here, the answer is -2. So it's 2 less than the original atomic number from the isotope. Okay, let's look here at another example. Positron. Here is the positron here. Notice the difference here. This is +1 this time. +1. And of course 0. So if you have carbon again, an isotope of carbon, 611 this time. Notice it's not 614 or 612 or 13. This is carbon 611. If it emits a positron here, what you would get is 6, and we're giving off +1, so this has to be 5. This is 11, and of course this is 0, so this has to be 11, because 0 from 11 is 11. As you know, the number of electrons determines the element. So you look at the periodic table, 5, and that 5 corresponds to boron. So this is the isotope that results when this isotope here, carbon 611, emits a positron. And here's a positron. Okay, let us look here now at the gamma ray. We mentioned this earlier, but as you can see here, the gamma ray has no numbers here or here, zeros essentially. So therefore the atomic number does not change, and the mass number does not change, but it gives off energy in this form. So we say that this is excited or in high energy, and then to come back to low energy or ground state, we call it, it gives off the gamma radiation. Let us look at another concept, or the same concept applied a little differently. This time it's electron capture. So notice the term capture here means it's now a reactant. So you add an electron to an isotope. What happens? So here we go. Here is the electron. We know it's electron because it's -1 and 0. So you add this to this isotope, beryllium 47. What happens? What is the product? That's called an electron capture, or the reaction of electrons with an isotope. What happens here is this is -1 and this is 4. So as you can imagine, 4 minus 1 is 3. And 7, 0, 7 minus 0 is 7. So the element, as we said earlier, is determined by the number of electrons. 3, you look at the periodic table, that's lithium. So we can make beryllium into lithium by bombarding it with, another term for that is bombardment, with electrons, or an electron capture, or we bombard or add electrons to beryllium. to form lithium. Okay, let's look at another concept, and this is called half-life. So as you can imagine, it takes time for an isotope to emit radiation to be transformed into another atom. And that time is unique for every isotope. So let me repeat that. That time is unique for every isotope. The way it's expressed in chemistry is called the half-life. So let us define half-life. The time it takes for 1/2 of a sample to decay. So in other words, if you have 1 gram of an isotope, the time it takes for that 1 gram to go to half a gram is called the half-life for that particular isotope. This is another way of expressing that same concept. If you have here 10 grams of a sample, and the time it takes to go to 5 grams is 8 days, so the half-life for this element here, or this isotope, is 8 days. Turns out that this is iodine 131. That's the isotope 131, iodine. 8 days. So after 8 days, if you have 10 grams of iodine 131, after 8 days you will have 5 grams. After another 8 days you will have 2.5 grams. So that's the half-life. Let us see how we can use that in calculations. So again, if you have 10 grams of a sample and you want to determine how much is left after 4 half-lives, or 4 half-lives. So here what we can do is, this is 1 half-life, 2, 3, and 4 half-lives. So you can multiply this out times 10. So after 4 half-lives, it is 0.625 grams. Or we can say 10 grams, 10 milligrams, and 0.5, same 0.5 here. And of course the 4 would be all of these. So if you have one of those calculators that can do x to the y, you can just plug these numbers in and then multiply by this, and you should get the same outcome. Here's another example. This time, what percentage is left after 10 half-lives? So you have an isotope, and you say after 10 half-lives, what percentage of that sample is left? So you have 100 grams. After some time, how many grams would be left based on the percentage? So 10 half-lives, as you can imagine, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 halves. Multiply that times 100, you get 0.098% that's left. So no matter what you start out with, after 10 half-lives, you will have 0.098%. Or, if you have one of those fancy calculators, put 0.5 in, raise to the power of 10, times 100%, you get the same answer. So you should be able to calculate half-lives. Let's see if we have a practical example here, and we do. The half-life of iodine is 8 days. So this is a constant for iodine, for this isotope 131. So that is a property. So iodine 131, its half-life is 8 days. That's given. In a medical treatment, which involves a dose of 400 milligrams, how much of the isotope remains in the body after 32 days? So let's make sure we understand this question first. 32 days. So in other words, you give this to a patient, and 32 days later you came back and do an examination to find out how much of this isotope is left, or this radioactive isotope is left after 32 days. You know you had iodine 131. You know from the table, constants, the half-life is 8 days. So 8 days into 32 works out to be 4 half-lives. So the question now is, after 4 half-lives, how much is left if you started out with 400 milligrams? Same calculations as we did on the previous slide. So what you need to do is pause the video here and of course determine how many half-lives are here, 4, and this is 400 milligrams, and multiply that out and see which one of these you get. After you do that calculation, what you should end up with is 25 milligrams is left in the body. So again, now you can see in the medical profession, we have to be very careful and make sure we do the calculations to accomplish the task, because if you give somebody radioactive iodine, for example, after X amount of days, you want all of it to decay, and that the radioactivity of the iodine 31 is not left in the body for too long. Okay, let's just summarize here by looking at some of the importance of some of these isotopes. As I mentioned here, carbon-14, the half-life is 5,730 years. And as I mentioned earlier, that's used in carbon dating. So if you have a sample and you know that its percentage of carbon-14 should be a certain amount, but it's not, you can determine how much it was sometime before based on knowledge of the half-life. You can look at this table here to determine some of the other important isotopes and their time for the half-life. Here's iodine again for 8 days. Just quickly here, some terms that you should be familiar with. The Geiger Müller is an instrument that's used to detect radiation. So you've seen on different news that folks that out in the in different areas, they checking for radiation. They have this little instrument that kind of beeps, and that's the Geiger Müller counter. Another one is the scintillation counter that's used to measure radiation based on what's emitted from the environment. So these instruments can detect what's emitted from the environment. Some other basic information here is that particles such as the X-ray and gamma radiation, a lot of times we're asking if they are dangerous. The alpha particle is not harmful to humans because it does not penetrate the skin. However, the X-rays, of course, as you know, penetrates the skin, and the energy of that radiation is a lot more than visible light, for example. Beta particles are less damaging, and of course gamma rays is another one that has a very, very short wavelength, high energy. So that's why it's considered dangerous form of radiation. So here just a little bit of information here. Carbon-11 is used in the medical profession for brain scans and so on. And of course you can just go down this list here. Here's another one that's very familiar, is iodine 131. It emits beta and gamma rays, as we have discussed, and it's used to diagnose thyroid malfunction in the body. So again, as you can see, the importance of isotopes to the medical profession. Lastly, let us look at transmutation. So in other words, here what we're doing is we take one isotope and we react it with another isotope, and let's see what happens. Of course, as you can imagine, this is called nuclear fusion because we're fusing two isotopes together. So here let's look at hydrogen. So remember, we have different isotopes of hydrogen. One is deuterium, 1 and 2. And we have here hydrogen 3 or tritium. And this is another isotope of hydrogen. You put these together and get them to react, as you can imagine, 3 and 2 here. And what happens is it gives helium here. Notice this is 4 and this is 1. So that adds up to 5. This is 1 and 1. That adds up to 2 because this number is 0. That's a neutron. But most important is that it gives off a lot of energy. 5.8 times 10 to the negative 8 kilocalories per mole. A lot of energy. So this process is called nuclear fusion, and of course the energy that's produced is used to generate electricity and useful. Granted, it's also used for the bomb, but here are some of the useful features of the energy that's evolved. Electrical energy. Okay, so you've heard of nuclear plants. That's all over that's different places throughout the U.S. Of course, as you can imagine, one of the downsides is that they produce nuclear materials. So that's a long-term problem, is that they produce these radiations and these different isotopes that are also radioactive. And so they're called spent fuels. And so that becomes a challenge for the environment. And so different techniques have evolved over the years. One is to bury it deep underground in the Yucca Mountain in Nevada. So they dig deep into the ground and bury it. Of course, the rationale there, if it's way into the ground, the radiation will not easily come out to affect humans. So this is the end of chapter 9. So for this chapter, these are the important aspects that I want you guys to remember, is that we have isotopes. Some isotopes are very reactive. The type of reactions that isotope undergoes is a little different from the reactions that we've done in the past. These are called nuclear reactions, where of course it involves the particles of the nucleus that's reacting here. And equally important is the applications to the medical field and of course to the environment and usefulness of the energy that's produced. So we'll have a quiz on this when you get back from Thanksgiving break. So enjoy your Thanksgiving break and continue to study hard. We are almost there at the end of the semester. You guys have worked pretty hard. So keep that up, just another couple of weeks and we'll be done. So I will give more information on the final exam in a communication to everyone. So enjoy the break and continue to study hard. Okay?